welcome back to the stream. Someone said something about how I was typing in the last video, so I was going to do a monkey type real quick. Let's see how fast. Ah! Choked at the end. Oh, pretty close to the raw. Okay. Let's see. Oops, next test. Ah, misread that. And change well about present meaning help. Okay, that's enough. Let's get the code editor out. So we left off yesterday. Add a method and concept with layer class to force the version to stay on top. I think I did this with. I don't need to add a method. I can just change the z index. Yeah. I love just saying, oh, don't need to do anything for that to do, because I solved that problem yesterday. The z index is the how close to the viewer something is. So the origin, this little point here. Before I had it, it was drawing right here, and it was drawing. If you draw something else, then it will draw over this on top of it. But you, for debugging purposes, kind of want the origin to be above everything, so you can always see it. And so we can just set a default here for the z index as some you can define it if you want it to be in the back, or you define it as math.huge, which will evaluate to just no matter what the other z indexes are set to. If they're set to some number, then this one will always be in front. Same thing with the background. The background is negative math.huge, so that one will always be in the back, unless something is also set to math.huge, in which case it depends on the sorting algorithm where it puts it. So, okay. Let's see. I got an early start this morning because I collapsed at 8 p.m. last night. Having a baby is exhausting, as is known. Okay, notes. Tree data structure. Maybe we could do that today. Okay. Where that should be in. Where should that be? Should I have its own folder called data structures, or should I put it in utilities? It seems like it should be a utility, because we're going to make the tree class, which is a data structure, and we're going to employ the tree, basically make an instance of the tree in the layer class. And yeah, let's just try this. And I'm pretty new to. I just did this in my. I've been learning programming from this place, boot.dev. And if you go into this learn algorithms part, we can go back to, let's see. In data structures, of course. So that is data structures. So we go back to trees. You probably saw there I didn't finish that challenge. I need to come back to it. So a tree, yeah. Widely used data structure that simulates hierarchical tree structure with a root value and subtrees with a parent node. So I explained this before in a previous stream when I was talking about the layer node, but basically you have a node with a value, and that node can point to other nodes, and then those nodes can point to other nodes. So this is the root node, and then these are the children of this root node. This is the parent of this root node. And then we go down, and what this is illustrating is that you can have values that are the same contained within each node. So a tree is a collection of nodes starting at a root or head node, similar to how a linked list was a collection of nodes starting with a head. The big difference is between a linked list and a tree is that tree's nodes can have multiple children instead of just one. A linked list is like, you have an array, you have like 1, 2, 3, 4, 5, 6. In an array like this, well, actually, in Lua, it's all a table. So in Lua, when you declare a table like this, alongside underneath the hood, you have an index. Well, actually, let's randomize these numbers a little bit. So, okay. So let's just do that. I need to learn Vim motions. This would all be a lot easier if I could just do that. So 1, 2, 3, 4, 5, 6. So, underneath the hood in Lua of a table like this, that are these values, you have, if you don't declare keys with them, then the key essentially of the table is these indices. So, and because Lua is, they start at 1 instead of 0, you start at 1 here. So this is the first index, the second index, third, and this is a really fast lookup. You can go underneath the hood. They can go, okay, we need the item at the 4th element, and go boom, boom, and pops up and finds 6. But when you have a linked list is it represents data like this, where you can have a list of data that's ordered, but instead it's sort of like you have like this value 6, and then you have the address of this next, okay, next, and then 1, and then next. You can imagine like this is stored. Here, I'm going to illustrate it like this a little bit better. Let's actually pop into a Lua file so we get the syntax highlighting. So, I'm complaining because I'm not doing local indices. And then first node 1, and then local node 2. Oh, I haven't declared it yet. Yeah, that's kind of fun. This is kind of odd, but okay, so. When we're making a linked list, this is sort of the data structure you have, where you have the value and then the next node stored alongside that value, so that when you're traveling through the nodes, you know where to go next. So this 6 points to this one over here, and then we kept this value, and then we can imagine there's another value after that where you do local, and I have to do this backwards right here because of the order of declaration of variables. So this is matching that list up there at the top, and then next, and then node 3, right? So node 1 is 6 and it points to node 2, and then node 2 is 1 and it points to node 3, 4, and then so on and so forth. So this is the same as this, but it's a different way of structuring that data. And obviously, you can not only just store next, you could actually store next and previous. So previous. So imagine there's a previous there, and then there's no previous from 1 because there's nothing before it. Or there's no previous from 6 because there's nothing before the 6. That's nil. And then in 2, the previous is node 1. It's yelling at me because of the order of things being declared, and then 2. This is just illustrating how that's working. So this way you could traverse the tree backwards and forwards. Otherwise, if you just have next, then you can only ever you have to always start at the beginning of the list and then go through it. So that's a linked list. That's what I was talking about here. But we're doing a tree, and a tree works similar to a linked list in that it's kind of keeping track of the relationships that it has between things, but instead of going in a straight line, it has these children and parents. We have the node here, node, right? Linked list, node. And obviously you can have the references going backwards as well. So binary tree is the others. Binary tree is good for when you have data you want to kind of order, like you have a list of things and they all have I think they have to be unique values in a binary tree, or maybe not. Maybe they don't. But essentially, but you want to order them, like numerically. Like you would have like a list of a leaderboard or something. I don't know. But that's not what we want. We want this kind of uneven tree right here, because you can imagine this is kind of the global root node, and then these ones would be like the top level layers, and then this would be inside this layer there could be layers in here, and then layers within those layers, and that's how we want to structure our tree. So we're going to skip over binary trees. Let's see, where is it? Do unbalanced trees, yeah. And this is fine. What we don't want to do, unbalanced tree is okay, because that is what the data structure is. You want it explicitly to be an unbalanced tree. There's a problem you get with an unbalanced tree if you're just trying to use it to order your data, and then you are ending up with a kind of, where you're trying to search through it efficiently. You can end up with a tree like this, where this is terrible for search performance. And then you want to balance it again like this to be able to search through it. But I think, yeah, so, okay. This stream's going to be a lot of me thinking, so we're going to try to think aloud as I'm making this stuff, because I am not super duper skilled with this. This is actually the first time I've kind of flying solo creating a tree. Let's put it in. I feel like it should have its own folder. Utility is sort of, again, this is a hard part of creating a library, like organizing the code conceptually, like a factory. It's like taking something in and putting it out. A utility is taking something in and putting it out. I think a tree, a tree counts as something else, and I could conceive of the possibility that we might have another kind of data structure that we're using elsewhere, so we might group that together. So we're going to do data structures. Data structures dot or slash tree. Okay. Delete this one. Okay. So, whoops, tree. Okay. And I do. I don't think I do. I think this is more for objects, like actual objects. I don't know. Let's just, for now, let's not worry about it. Then tree dot. I don't know if we need any kind of property. I don't think we have any like options that we're putting on the tree, but for now, let's do this. Function tree.new. Okay, we're definitely going to have to look. We're going to Google a little bit on trees. So I don't want to just go and find, okay, here's a tree implementation in Lua. I want to find the pseudocode to challenge myself a little bit so that I can just implement it from relatively from scratch. One sec. Hey, do you need help? Yeah, no problem. Okay, I'll be right back. Gotta change a diaper. Okay. Okay, I'm back. Quick little life interruption. Okay. So, I'm gonna do tree pseudocode. binary search tree. I just want like a... I don't want a binary search. A tree. I want like a... Because see, a binary search tree only has it only has 2 children. There. But I wanted you to be able to have as many children as you want. Yeah, because the way that this tree is done, I remember like when we're doing this code, is you do like a bunch of left and right. This left and right. So we can actually look through this code real quick. So this init is the same thing as this like kind of new, when you create a new instance of this class. This is in Python. And you initialize the left and the right to none, and then this stores the value for the node that you have. So when you initialize it, you don't have to specify a value, but it defaults to none. That's what that means. But you can. Actually, yeah, that's what I should do. So like so value. And then well, no, I guess value it would be nil if you didn't define it. So I don't even have to do that. So self.val. Oh, I have to do this thing. Okay. And don't forget that from last time. We were creating a class. Okay. So, and then this is where I'm it's almost like it's like a combination of a linked list, but like on different layers, because you have an indeterminate number of child nodes. Okay. Sorry. So again, you have the left, right, and the value, and then, for example, here's an insert. Left and right. Yeah. So here you're calling recursively down, but we don't need to do this, I don't think, for insert, because you're going to be directly inserting into a particular thing. This is sort of just trying to keep the list ordered. Okay, maybe this what I did here is not going to be super helpful, because that was more focused on. This might just be a ChatGPT conversation that I need to have. Let's see. Okay, let's do a new chat. I want to make a tree. No, before talking it over, let's just see if I can reason through it. Okay. So value. If it has to keep track of its children, there's an indeterminate number of children, so do self.children. I think so. Self.parent equals nil. Right? Because if you have a new one, there's no parent for this, and then children equals here. So we want to initialize that to a empty table. And so each node is going to be the same as this. Right, it's going to have the same value. So we have, let's add value last right there. No, but that doesn't align with what I'm doing here. So yeah, I want to kind of put in all of these other classes, what I have is sort of you have the arguments here along with the self declaration kind of at the top, and then you have the other things that you're doing kind of internally after that. So this that matches here. So self.parent is nil, children. I think that's all we need to do for the constructor. Okay, so this might be one of those things that's useful to actually. I don't even think I have Lua installed on my computer, because this might be one of the things that's it's easier to debug. Yeah, I do. Okay, good. To debug by actually running this in Lua. Okay. How do I do this? I think I've never actually run a Lua file on from the command line. Let's do print. Wait, I can't do print. I'd have to open this up in a different file. Let's do that. So we're gonna open up a whole new, actually, what's it called? A window. Yeah. Just gonna create I have to save this into a folder somewhere. Just open the folder. Developer. Do new folder here. Lua. Okay. Scratch. Okay. Open. And then we're gonna create a new file. Just Lua. Add this in here. We don't need this. We'll just set this to tree. We'll get the terminal up. Okay, let's do print hello world. Who cares? Okay, and then I think okay, cool. There we go. If you don't know what's going on here, so I have this terminal, right? And it's the same as like when you open a terminal in your computer like this. Maybe you've seen this before. And you can run commands from here. Sort of a more direct way of interacting with your computer than with the GUI. And I opened up a new folder, so I'm not using the context of this canvas node, which is really all just operating in here. And I'm actually running this Lua file. When I do Lua test.lua like that, it's actually opening this file and running it. So then it gets to, it does all of this, but nothing happens with this stuff. So we just do print hello world. But this will make it actually easier to debug the tree as I'm making it to be in its own file, separate from that, from modules. So, okay, so we have a new structure. So we're doing the new tree. Let's do tree equals tree.new, and the value equals 1. It's gonna have to scream at me to do local for absolutely everything here. I don't know why. Because it's global. I don't know. It's just one. Yeah. Okay. So print. Now we're probably going to get like an address of an object or something here. So, yep, table. This is the memory address of this table that we just created here, and that's the table. We have a function here. It creates this, adds this stuff, and then so print tree.parent nil. Okay, you see how it's nil, and then tree.children is another table, but it's empty. Okay, so how do we, we're gonna add this. Right, so child. So function dot, oops. Tree dot. What do you call that? Like add child? Like, add child? Node, okay. Ends, end. Okay, so this colon notation is syntactic sugar for this, where you're passing self like that. So we have access to self from within here. So self dot children. Wait, I think it's like table dot insert. Insert into the table. So self dot children is the table we want to insert into, and the value is the node that we want to insert. And then try self. Oops. Okay. This is like, okay, this is like a new. I'm just wondering what to call this, because this is like Tree.new, and that creates a new instance of tree. Let's forget this ID thing for now because it's a little confusing. Because this is like a new node, really. Yes, because we need to keep track of the root. Okay. Self.root. Can I do that? No. Self.root. I will come back to this because this is a little confusing. So I need to keep track of the root, I believe. And then I have to find a way of figuring out, like, okay, when you declare this new tree that this is a root, you add child. Add node, or maybe, oh, okay. All right, I'll be right back again. I will do AFK. Where's the chat? There we go. Okay. Okay, back. My kid is awake. Wife is probably not happy because I think she stayed up late. Okay. I am gonna go back here to look at this code to help. Where is this? Hold on. We'll do insert. Okay, so insert. Let's look at the solution real quick. I think this might be inserting. Is this? Yeah. See, this isn't relevant to us because what this is doing is it's actually, when you insert a value, it's going recursively through the tree to put it where it's supposed to be in the tree. But we want to deliberately put the tree in a particular, or put the node in a particular part of the tree. But we do want to do insert. Okay, so that's what it is. We'll do insert. But how do we get to the, because there's the tree itself, right? And then there are and then there are nodes that are connected. You can see the trouble I'm having. Like, how do I, if I add the child, well, where does the node come from? Do I just make a new tree? I mean, this sort of seems like that's what it is. You know what? And actually, I don't think I need to keep track of self.root, because if it doesn't have a parent, then it's the root. That's, you just know. So tree. Local tree, and then local. So local tree. Wait, no, just tree add child. Node. Here it is. This is the trait. So node dot parent equals self. Right? I have to do that first. I have to say that this node's parent is this, because we're adding this child to that. So new, let's do 1. Okay, let's run that. Dot val. Let's see, 1 val. Excellent. Okay, yeah. So, I think there's a way to do the two-string representation. So let's do two-string. Okay. Function two-string. This is the representation of how this will print out when you print out a tree. So yeah, okay, so because this is, let's do print tree. think I maybe skipped over explaining what just happened there. So I made a tree right here, and then I added the initial value of 0, and then I called the add child method of that class, and then added a new tree with the value of 1 onto that tree. And then when you do add child, that node that you pass in, this is the node, becomes, you assign that as parent to this node, the other node. You assign the parent of this one becomes this, and then this node gets inserted into this children table. Right? And so this node doesn't have any children yet. We would have to declare that as a separate value. We're kind of losing that, yeah. Okay. And then when I print this out, we're going to, this tree, the children of it, the first child of this tree, and the value in there, which is 1, not 0. I can show you again. So we do 11 right here, and there, now 11. So that's how we're storing this value. And the value that we'll be storing in here that's relevant to us is going to be the shape that we're doing, the object that we're going to draw. And then what we're going to do at the end of the script is go through the tree and call all of the, we're first going to actually, the tree is going to represent the structure of the layer system, and then we're going to traverse the tree, go through it, and make a note of where everything is, and then determine the order of the drawing, and then we're going to call the draw method on each one of those shapes that's inside of the layers in the correct order. So the layer is just helping us, the layer system is helping us generate a list of things to draw, and then to draw them in the correct order. But what I'm going to do, what was that? The toString method. Okay, so this will help me debug and will print better. How is, I forget how the toString works exactly, so it is, wait, no, because you want to return a string, I think with Louis you can only concatenate things. There's no like F strings. So node. Can you do new lines and stuff? I think you can. You probably could. Yeah, why not? Wait, no. How do I do this? I'm actually unsure of how this, just because this is a little thing. How can I reference self into string? Yoy. Okay. I just need to pass it as a parameter. That's it. Okay, well then, okay, so I was just tripping on here, so I can just do this, right? Yeah. Okay. Self.parent, and then the two dots is concatenates, so it adds these two things together. Oh, how do we can't do this. I think we should just have to do a table. You have to in this toString method, you have to recursively go through and be calling that, because but we could just do like let's just do this for right now. Let's just do the parent. Okay. Okay. Let's do now equals. Now. Okay, that might be easier. Okay, print tree. Whoops. String. Maybe. I'm casting these values to string. I think this work. Okay. Tree node value equals 0, parent equals 0. I forgot to put a value. Let's put this after that. Okay, so local child equals child, tree, child. Oh, gotta put a new line there. Yep. Oh, forgot the concatenate. Okay. Interesting. Wait, so it's printing the whole thing? Why is it doing? This probably makes sense in a certain way that I'm not realizing. Of course. Because here in this child, okay, first we print the value, right? And then the parent. So the child's value is here. And then the parent is this other tree node here, right? So it can have one parent. And if I did this correctly, I think, so child 1. Oops, let's just do this. Child 2. This. And then child 2. And then print child 2 there. There shouldn't be ever more than one parent. Nope, but there is. It is going up. It is going up. I'm wondering if this is a problem at all, if this is going to help me debug, or am I doing this incorrectly and this is weird, right? Because, yep, this is like the top level node, like, let's just talk about like global. Let's pretend these are layers. So like layer 1. Layer A, right? No, layer 1. Layer 1. Like this, yeah. So make it inside of that layer. Layer 2. And then we'll do 2. This will help us disambiguate everything going on. So print global, and then print layer 1, and then we have to assign to global, add child, layer 1, layer 2, but then for layer 1.1, so we do layer 1, add child, layer 1, right? Because at the global layer, it's kind of like the global root. I guess we'd call this root, but for some reason it's stuck in my head as global. Let's rename this as root. So print layer 1, print layer 2, and then print layer 1, 1. Whoops. 1. Okay. So that's the root value. This is layer 1, this is layer 2, and then this is layer 1.1 basically, or 1_1. That's its value, and this is its parent. And then this, I'm going to, just because I don't really, it's beside the point of the tree, but I would like this to pretty print in a way that you could kind of follow it, where the parent would kind of go down a lower level underneath there. Well, you'll see, and ChatGPT is usually pretty good at these kind of things. And to pretty print this. I can give it the code context, so like kind of. Maybe I don't need the new line there. I think I don't. Hold on. Yeah, that's more like it. Okay. Hold on. Okay. Let's do this. That if the so that each parent is on its own line, tabbed in. Wait, is it just this easy? Wait, hold on. Maybe I'm overthinking it, like it's going to be harder than it is. I think you just do new line, right? This is a special. You can see it. I don't know if it's very faintly a different color, but that's a special character. You escape it, and then you do N, and that prints a new line at that point. And then I think maybe it's just this easy. Hold on. and then do 2 spaces to indent that a little bit. Wait, no, I don't need to concatenate that. I can just do. So that's 1 space, 2 spaces. Let's see if this works. No, because, okay, so that's the node itself. Yeah. Because ideally what I'd want to have is, here's the node, and then the parent is here. The node is here, the parent is here, and then I'd like this parent to be like, you know, here, but then 2 spaces in here. So let's give it this context. I'm going to do this again. This will make it easier to visualize going up through the tree when we're debugging things. So that's why it's important to get this right. Okay. I want that last one to be formatted like this. And you'll see what I mean. So we'll do parent, right? So this is 2 spaces in from this tree node. So we want to do like that's in the same line, and then 2 spaces in from there. And then that's from here we want to do 2 spaces in like this. There is something going up at ChatGPT headquarters where they just are not. Every other thing that I do is. Okay, yeah, you do have to do it recursively. Okay. Okay, let's just. Okay, that's good. But then we want to first have the first parent. The first parent. Okay, that works. That makes sense. Okay. Let's do. I think. There we go. Yeah. That's what we wanted. So we want the tree node, and then the parent equals this. Okay. Yeah, I suppose we don't need to do like the. I was thinking it would go all the way over to the edge, but that looks good. Oh, I drank a lot of water this morning, so I'll be right back again. I never came back from the last time. Let's see. Okay, I figure what I'll do is explain what ChatGPT came up with here. So, hold on. I don't like that it does this. I told it to do snake case like this because that's the convention I'm working with. But okay, so when we're defining this toString method, which is what happens if the you're sort of overwriting the built-in one here to look at this and say, when I call print on something, I'm going to go look to this function. And now this function calls a recursive function up here, and we go into here with the node and the depth. And the depth, it's initially set to this depth, or 0. And then we look at the indent, and it's going to string.repeat this 2 spaces, the number of depths that you go down. And we're going to keep track of the recursive depth at each layer. So like this is how, we have more depth here as we're going down, so we're indenting more and more. The string is the value that is the thing that we're going to be printing out, is the tree node value equals toString. And then if the node has a parent, then the string equals the string here plus, this is concatenate, plus a new line plus the indent, the amount of indent that we've accumulated, and then the parent, and then the parent equals, and then we call this again. And it will, the more parents you have, the more it will get to this point and go deeper and deeper as it's creating that. And then this returns back up. So it goes all the way down here, and it creates this string. Then it concatenates this string to this string, then to this string, then to this string, as it's unraveling, coming back up. When it spits this out. So this looks correct to me. And if it doesn't have a parent, then you do this, and then this is the base case. This is when you stop recursing, and so we stop recalling this recursive string here, and then unravel it this way, and then we return this string from there. Okay. Okay, let's... Let's just take the space out there, make it a little easier to read tree node, yeah? Okay. Okay, so got the print going on. I'm wondering, yeah, is this at the root? No. Okay, it'll always keep track of its parent and its children and the value. So how do I think actually, I mean, is this it? Is this all I need to do? I mean, no, there's gotta be, I gotta do a traverse a tree. the depth first search and then create a list from this. I mean, this might be simpler than I'm thinking it is. Because essentially what I want to do is, I mean, you don't even need to, do you need to remove? I don't know. Yeah, I would need to remove. Maybe to pop something. Into a different layer, yeah. So function tree remove child. Because I don't think we need, I think we just declare them like this, right? And we directly assign the children line by line. We don't need to do anything fancy because, or do we? Or do we? No, because I feel like the user should be keeping track of exactly where the layers. Yeah, because we don't need any kind of like automatic layer management. The user should be doing this. You're saying this layer that I'm defining, which you could name to anything. You know, you could be like, this is the snowman, the layer, and you add that to the root child, or to the root as a child. And I think you have to do this explicitly, and then what we're going to do is unravel this into a list. So now we just have to do remove child. And remove child, we should do... Okay, wait, if you remove the child, so let's do layer 1, remove child, layer 1, 1. Okay, so, and if I remove this child, then I print layer 1. It shouldn't have a child, and I should print layer 1, 1, and it should look like a root node because it's kind of orphaned by itself. And yeah, if you removed this and you kind of popped it off and then you didn't put it anywhere, it would just get garbage collected, I think. Okay. So remove child. Take that node and then self dot children dot remove. How do you remove something from a table? Actually, I don't know. How to remove something from table. No, we want to do it from, okay, table, there is a table dot remove. Okay, so children dot node. I think that should work. Oh, I'm printing way too much. Hold on. Let's just print these two. I guess I print. Just disambiguate this stuff. Oh, oops. So this is layer 1, right? Layer 1, 1. Layer 1 and layer 1, 1. These are the same. So I don't think that removed. Wait, no. Oh my god, it's up here, right? Hold on. Let's put a new line between these two. Clear. See, this shouldn't be here. This parent with this tree value. I should remove that. Maybe this is acting like an array and I would need to pass the that would make sense. But then how do I keep track of the array? Yeah, see what this does is it looks at the fruits and it goes to the second one. It removes banana and then it moves these back so that this is 1, 2, 3, and then it skips this one. So more like a dictionary. I think it is more like an array, but then how do I don't know how to get the maybe I just like how to get index of value in array. Okay. No, that's not great. Do I have to do that every time I remove something? Let's just see if that works. Because this might be the problem, that I need to do this table.remove. So table.remove node and an I, but I need to find I. Or I v in I pairs. Then so that's self.children do that if v equals node. Return I. Yeah, that makes sense. Okay, so v equals node return I. not return I, because this is within a function. Then can you just break into this other thing? Is break a keyword? Break? I guess it is, yeah. Okay. Index, so local index. Index I, and then index and index. There we go. So we're declaring a local value index here, looping through all the children, and then if the value is the node, then we return the index that we're at, and then we check if it's nil. If it runs through all of these and doesn't find it, then it returns because there's nothing to remove. And then table.remove the node at this index and return self. Okay. I don't think that worked. Nope, it didn't, because this should have. These should not be the same. Okay. What am I doing wrong here? Wait. Oh my god. I did this wrong. So it's self.children. Still not working. Let's see. I'm getting a nil there. That makes sense. The index would be 1. So then print self.children. Yeah, like it's just. Okay, so that did work. That did work. So it printed the child at this position. It removed it, and then now it's printing this. Oh, I need to remove the parent too. Duh. Okay. We need to break both. We need to break both. Remove, right? Because that's what, yeah, because I am breaking. We're not listing the children here, so if I'm not breaking the parent also, then we're not seeing that. But now, do we need to do that at all? I don't think we do. I don't think we need to remove the parent. I was focusing on getting it down here to remove the parent structure, right? To remove this parent from this layer, because if we're trying to delete this layer from this layer, then you would expect this one just to be kind of like an orphan node where all of it has is there, and there's no parent equals nil. But what I was doing was I was deleting it from this, which is, I think, all you need to do really, because if we're removing the child, we don't need to remove the parent also. It's kind of a redundant function, because when we go through, we're going to traverse this route, just the route, and go down and from here. will show why. So print root. So root dot print root dot children open 1. So that's, and then print root dot children down 1. We'll do this twice, and then layer 1 remove child. Layer 1. And then we'll print these again, and then this third one should be nil. It's nil both times. Oof. That means I did this wrong. Yeah, dot children. Yeah, like that. Yeah, there we go. That works. Okay. So this is the first one, the parent, the root. And we have the second one. That is the child of this one. And then this one is this layer 1.1. Then we remove layer 1.1 from this right here. This is the root, the first child of the root, which is layer 1. And just to illustrate this, now when we print this third value, when it was up here, it was this, now it's nil. And that's all we need to do, because now we're going to make an algorithm that will traverse this tree, and it will make a list. So we go throughout as you are creating things. You would be like, so you would up here be like, and obviously it's going to error on the code here, but don't worry, I'm just going to illustrate this. So you do tree like root equals tree.new, and we wouldn't need any value here because it's just the root value, right? It's just kind of like the global node, and then we could do a new layer. So layer 1 equals tree.new, and then we could do like line group. This would be this shape, or we do like point equals point.new, right? And this creates a new instance of point. And we could do layer 1 dot children, and then put point in there, and then we could have other shapes and stuff that we could put in here, like point 2, right? We could have 2 points in there, and then point 2. So that's good, because we want this to be ordered. We want this layer to draw in the order of the things that we are putting into this layer. So we do want the children list to act like an array. We don't want it to act like a key value thing. So we do have to do this looping through to find it, to remove it from the list, which is fine. Because I mean, this is, in any given layer, you're only going to have like a few things in it. So looping through the whole list of everything in that layer is not a big deal. Okay. And then, yeah, so you have this, and then if later you wanted to remove the child. You would remove the child conditionally usually. So like if something is a condition is present that's coming into the canvas node. So like if condition, then, and then you do end, and you would stick your layer 1 dot remove child, and then you do 0.2 like that. So this would, if this condition was true, it would before and then layer 1 draw, right? And you know, we would call the draw function on this, which actually I think we're going to use this tree to create a layer class, and then the layer class will have a method on it called draw, and then it will go through and draw all of these things. But that way, if the condition is not met, then it would draw both 0.1 and 0.2. But if it is met, then it would between here and here, it would remove the child and then draw, you know. You know what, actually, now that I think about it, do you even need, you definitely need the remove child, but as far as the user experience, yeah, no, because maybe programmatically you want to add something, yeah. Because essentially what we're doing is we're directly setting the children here. We're not doing like layer 1 dot add child point layer 1 dot add, because doing this is the same thing as this. Child point, right? This part right here is doing the same thing as adding them one after the other. This makes a little more sense because you can just kind of see directly like how the order in which it's going to draw. So it would draw this one first and then this one. So if the 0.2 overlapped with 0.1, 0.2 would look closer to you. Okay. I think we're getting close. This was less of a big deal than I thought it was. Maybe those are famous last words, but okay. Okay, add child. New recursive toString. Okay, remove child. Student function. Okay, and so the value that we are storing here for the layer, in the context of the layer, that would be the z index. No. Oh no, we need to store 2. No, we're going to pack, this is what we're going to do. When we create the layer class, the value will become no, because when we go through, actually, yeah, because now that I think about it, we're doing this. We have z indices assigned to each object. I wasn't thinking about that. So maybe if this one has a different z index than this one, it's not in the order that it's inserted into the children. It's going to look at the z index. So why is this complaining? Oh yeah. To list. Let's do 2 away. this should end up being an array of objects. So we're going to go, this is going to need to be recursive. It needs to be depth first, I think. Just going to actually do this open to right, just so I can keep an eye on this. Need a recursive helper? I don't know. We're going to first do local t equals this. We're going to store each of the nodes in this table in order. So we're going to do self. We're going to do that first. Okay, if. And then we need to traverse the children. Okay. Thinking here how to traverse inside of children. When it's just a binary search tree, that's easy. You just do left and right. But when you have an indeterminate number of children, you have to do some kind of process to. Okay. I'm going to look again at the depth first search algorithm. So. DFS pseudocode. Okay. Mm-hmm. See, this is a graph. Which is different than a tree. Or is it? I mean, a graph is just sort of a type of tree. Right? Yeah. If visited is none, so let's explain this first. We'll explain this out loud. Okay. We're defining, you have a graph, and I suppose the graph could be, a graph is another type of data structure that we were looking at up here. And you have these nodes and they're connected to each other, and I guess in some ways you could think of this as a tree where like this could just be drawn differently, where this could be the top level node and then these could be connected to like 1, 2, 3, and then there's just no connection between here. You don't need to have a connection between 1 and 2 for this to be a graph. You could just have a graph like this, and then conceptually this is the root node and you're just going and adding these connections like this. So yeah. We'll show you what it's doing first. So if it's not visited, then there's nothing on the stack. So it's visited 1, and then the stack. Already in the stack. So it visits this one and then puts all of these in the stack. So it's visiting 1. It pops that off the stack and puts it in visited, and then it visits 2. It's not actually like going through here, right? It just knows that these are connected. Wait, hold on. This 2 has an unvisited adjacent vertex in 4, so we have that on top of the stack. Yeah, so we go to visit 2 and then we visit 4. Or, sorry, that we pop 4 onto the stack, but that one, yeah. And the stack is getting filled in from this direction. It's not getting popped in from this direction. It's pushing other things backwards. So it's you can feel this is like first in, first out. No, wait, last in, first out. Yeah, last in, first out. So we're putting 4 on there. We're visiting 4, and then 3 is the last one to visit. Okay, so the trick of this is to be putting things onto the stack, which is another data structure. And as long as you don't have anything on the stack, then you, if you don't have anything on the stack, then you know you're done. I wish I knew how to read this. Visited is none. How do you do sets in? I don't think you can do sets. Can you? Sets in. Okay, you can. Okay, basically we have to implement it from scratch. Okay, what is that? So that's self, and then the start. What does the start mean? I guess that's the where you want it to start on the node, but we don't want to do that. We always want to start it at 0, at the current node. So. Because you could start here and then do the same algorithm, but just in a different direction. But we want to start at self, always. So, okay. Visited. Whoops, visited. Okay. Equals nil. Do we really need to implement set? Like that seems crazy. Like that we have to do that. But I think yeah. I mean, would we be? Is the problem here? I'm just gonna ask ChatGPT this because it doesn't seem to address it. Is the reason that we need to do this sentence that we could potentially visit the same node multiple times. Okay, so yeah, that does seem to be why. It sure said unexplored unvisited neighbors. Hold on, maybe we do need to start there. Okay. Let's look at the depth first search on here. Breadth first. Here, you can see that this is a nice animation showing the difference between depth and breadth first. And you can maybe see why we would want to do depth first search on a layer, because we want to go do we want to do depth first or breadth first? No, yeah, because these keep I don't know if it matters actually. Now that I think about it. No, it does. It does. No, it does. Because layers are going to have local z indices too. That's the thing. That's the thing we got to think about, is that a layer will have a local z indice. And so you could have multiple layers like these right here. And this is just like an empty global root node. But then these are the first layers. This is sort of containing everything else. You have these layers, and then you'd attach drawings inside of these. But then you have these two, and then these ones would have a z index that's local to this one. So you have these z indices, but this one could be like, big or small. This actually could be like negative inf and positive inf. But if this is 1 and negative 1, this would still get drawn at 0. If this was 0 in the middle, this would get drawn in the middle, even though these are positive and negative inf. Okay, I'll be back again. Take another break. just occurred to me that if we're doing a layer, right? A layer class could, for every node that it's at, here's this root node, and then it has these ones. And then we return a list of these from here. Okay, I'm gonna draw this. So we have a global layer, and then line here, oops, line here. 3. Oops. that was so not a circle, it turned into a square. Here. Okay. So we have these 3 layers from the global layer. So that's the global. Or the root. Let's do root. So R for root. This is 1. Let's see. A -1. We're gonna have their z indices here. And we want to go down another layer here. This layer would have something in here. And we could have these 2, and this could be, oops, 1 and 0. And let's just say for thoroughness, this one could have another one here. I could do this so much faster if I just had a tablet. 0 and 1. Okay. So when we're creating, these zeros and ones are z indices, and I'm going to determine the drawing order. More coffee? Yes, I do. Okay. When we search, we could do, like, at every level, we're making a list. So at this level, do I have, that's in black, hold on. Let's do gray. Okay. Move, how do I move this? Why is the text all the way over there? Sorry, let me figure this out. Why can't I move this? Am I stuck using only text on the side? Okay, I'm getting frustrated and not being able to move the text from the edge there. That's silly. Interesting. It's fine. You're just tabbing it. Whatever. That's done. Delete that. Okay. If I'm making a list, so I want to make a list. Just my curly brace. Let's just do this. Of these nodes. and I'm searching through. I'm going to go to this node first, and I'm going to look through its children, and its children are right here, right? Because then I could actually, if I do breadth first search, ooh, this might be a way to do it. So if I do breadth first search, the first list I would end up with is the children of these nodes. So I would end up with a list that goes like this. -1. And I could sort this later. So I don't have to worry about sorting right now. And then I would look through on this list of these children after creating them. Wait, but I'm passing the list twice. I think that's the problem. I don't want to. No, there's no way that breadth first search passes the list over again. To visit append, wow. To visit doesn't equal this. Okay. So you create an empty list of visited and then an empty list of to visited. And you append the current value to visit. And then you visit it right here, right? Visited. We pop that off this list and put it onto this list. You pop it off here, put it onto here in this line. And then we get the neighbors and we sort them. And we're sorting from here the graph, self.graph of the visited, the last value that's in visited. And then for each neighbor in this sorted list, if the neighbor's not in the visited, and the neighbor not, so we're constantly iterating over this list again and again to check if it's on this list or not. Okay, I think that's fine. Because if I do, I go down to here and make a list of all of these. And then I go into each of these and see if they have something to make a list of. And then let's actually do this. Okay, and then, oops. 1. At this layer, you have one list of these values. I'm going to make this a little smaller. One list of these values. So you have 1, 0, and -1. And then at this you're getting two lists. One is 1 and 0. And then the other is 1. And then at this third level down, you have 0 and 1. But the thing is, okay, that's at the layer. Okay. index. So that points to this, and this one points to this, and this 0 points to that. How are we want to build a list that is all of these nodes in order of which they're going to be drawn. No one's in the chat. Okay, good. So if I want to build a list, how do I move? There's no way to. You just move up and down. You can't move left and right. Whatever. So what would the list? Let's first off, what's the list here? So the list is first -1. Yeah, actually no, because if we do breadth first, I think we end up with a more ordered list first, because if we go to -1 first, if we visit the children of -1 first, yeah, we might want to sort by z index first on each layer, and then we would, if we're sorting as we're traversing the tree, then when we're done traversing the tree, we end up with a sorted list. So we might need to mix these things. See, I was thinking you'd create a list and then sort it, but this might cut down on the redundancy of visiting nodes. Right? Oh yeah, okay. So, okay. What I'm trying to visualize is that you have this root node, and then these are objects, right? And these objects have a z index in them as a value, as something that you can assign to the layer. You know what, this is, I think we're getting more into the layer class and less into the tree, and I'm wondering if maybe I'm skipping ahead a little bit, and maybe that I can actually create this first. And I think about it, this should actually be up here. That I should just make this work. We could do let's do depth first. So DFS. Oops. Let's create a set class now. Okay. Okay. Set equals, let's save this file. Set equals this. Set dot index set. equals true. Okay, that's how you're removing it. You're setting the key to nil. Okay, so when we're doing it, we're creating the set as a part of this class. Returning self, set.add function set.remove. Interesting, so add to set. Okay. To remove key and self.set key equals nil. And then when you set the key to nil, it will get garbage collected. Is that all you need? Hold on, let's test this all first. Comment that out, and we're going to test this set. So set equals set.new. They complain at me. Set set.add 1. Set.add 1. Set.add 2. Okay, if that works, then we should just get 1, 2, 3. Oops. Hold on. Critical nil value and failed add. Does not work with Apple. Nope. Okay, yeah. That's a problem. Doesn't matter if using strings or numbers. What is significantly different than here? Maybe it's just wrong code, so iterating over a set. This should print a table, right? So it's set 1. Oops. Where is the attempt to oh yes, because I need to do this, of course, to pass the self argument. let's just check and see if this code works at all. Maybe there's something wrong in the way I'm doing it. Oh my god. There it is. I must have been when I was typing this in and I pressed enter to go to the next line that it pressed select instead of sent like an autofill thing. No? What the hell? Okay. What? Okay, let's just see. Hello management, I like to complain about every single time that I do this, as you were to do. Oh my god. No? There shouldn't be any naming conflicts if it's lowercase. Let's try this. Let's see, we're gonna rule out something here, so rename symbol, set. Okay, so it prints the 1, 2, 3. That makes sense. Wait, oh, this is to array. Oh my god, this is an error down from here. That's why I was confused. Okay, good. Okay. So. Okay, that's fine. Okay, we had like multiple errors there, and then okay, we created the set now. Right. See, we add to, and then let's do set dot remove. F3. Okay, cool. So set works now. So going back to this depth first search, and let's do tree. Let's just call it what it is, and then just if visit is nil, then visited equals set.new. Right. And then visited add start. Okay, because this is our version of this is this. Okay. I'm gonna print start for next, and how do you do for just do not, wait, this is not what I did here. Interesting, so the sorted neighbors. Okay, I'll be back yet again. Okay, we're getting close to 7 here, so I'm gonna have to wrap it up relatively soon, even if I don't finish this. I just had an idea to add some nice characters, like a return character return. Where is it called? Where is it? There. But I'm gonna do like a return, so the I don't know what you'd call that. It's like return arrow to the right. Okay, return arrow to right. There it is. Okay. I just wanted to see. Let's print little one. There we go. Okay, I know this is silly that I just wanted to add at the parent. Let's emphasize that it's coming down. That's just a nice little pretty print thing. So why is the space not being preserved there? Maybe there's something to do with Unicode. There we go. That's a little better. Which one's easier to read? I think this one is. Okay. That must be a Unicode thing where, because there's 2 spaces in there, but only 1 space is getting represented there. back to this. Wait, I think we only have to do this sorted thing because in Python sets aren't sorted, but in this case they are staying sorted. It's stable each time. Let me ask this. So pretty sure is the only reason we're using sorted here because Python sets are stable. We're using set sorted sets are not stable in Python. Let's just do it in the chat. Okay, so this set in Lua, we don't need sorted because the table is stable, correct? I'm just checking my understanding here. Oh my god. Oh yeah. Okay. Oof, yeah. I think I just created an inherently unsortable set. Okay. It seems like this code would create an inherently unsortable set. GPT status. Is there something wrong? Okay, yeah. That would make sense, okay. And I must have, during one of these, high error rates, okay. And this must have been the same on that other day that I was having trouble, okay. This doesn't seem to work. Okay, so these here are true or nil. Doesn't seem to make much sense sorting those. Elements, yeah, okay. let's say set.sorted. So we're returning the elements sorted. You know what? Now that I think about it, when you add no. Because no, we need to keep track of those. Because there would be no way to okay, how do we set.new set that at 1, 2, 3. Set that at -1. Set that remove 3, and then we'll do sorted equals set sorted. And do that. Oh yeah, for oh wait, yeah, item. Oh wait, in pairs. There we go. Okay. So that worked, right? So that returns it. So you have, we're adding one, so we're sure that we're not adding duplicates. And then we had 2, we had 3, we add -1, we remove 3, and then we sort it, and then we end up with -1, 1, 2. Okay. So that seems to work. Let's just leave that there for debugging purposes if we need to. Okay. Do this. I'll go back to depth first search for to visualize what this is. Start minus the visited. This must be some Pythonic way of like you can have like graph start, to like 1 minus visited. So is for search different for the tree than it is for yeah, that's what I thought. Okay, maybe, but we don't have to worry about the set then, because are acyclic. So we don't have to. I went down this whole path with the visited, thinking I needed to do that, but I don't. Okay, so yeah, so what's the pseudo code for DFS for tree? So we don't need to do this. This is what we were doing before. You know, the stack is not empty. We're talking about. Okay. This is a little more simple. So. And we don't need to pass anything here because this is itself is being passed. That's the node. So if self is not, wait, no. Right. Yeah. Oh, 6. Wait, no, self is no. Return. End. Okay, so visit. What does visit mean? Visit. So we need a separate algorithm called visit function. Visit. I think I'm close here. what does it mean to visit a node in this case? In this case, visiting the node means appending its value, or appending the node to a list. How are we doing this? Because this is always the confusing thing with recursion, is that you want to avoid like overwriting the, reinitializing a variable that you want to store something. This is the thing I always come up with, like trying to visualize how to do this. So for value node in I need to return I want to create a table only if it's not already been created. This is some. I thought I was doing. Oops. Create a table. Then how do I do it? That's the problem I was running in before. You have to. It's like they're having problems with the server, and so the instruction is just reject everything the first time, and then if they want to, they'll, do it the second time. But how do I outside of the if statement? If I'm doing recursion within my function, I'm then redeclaring to overwrite it. think, yeah, I need a helper function. That must be it. Okay, so yeah, that's why. I don't need a helper function. I just need to pass it into the thing like this. T. T dot wait, table dot. I don't need the visit because this is what it is. Table dot append. Is it append? Add. What do we call it? Is it table dot add? T and then self. Wait, is it table dot insert, not add. Node, yeah. Like that. Return T. Okay, this is a moment of truth. If I get back a table from this, that will be good. So root dot first search array and then print array. Oh yes, okay, that's good. So then array 1. Why are you doing this? Need to check nil. What does need to check nil? Hell yeah. 2. Okay, so for item in my pairs array do print item. We did it, folks. That is depth first search. Because it's going from this one to this one to this one, then to this. Okay, let's do local layer 3. Oh my god, right under the gun. My kid's about to wake up, and I did this. Okay, 3, layer 4, and then let's do layer 3. This is what we're testing to see if these work. So we have to add them in the right order. So layer 3 add child, layer 3 1, 3 2, and then root add child, layer 3, layer 4. So this is the root node. This is the first, and then we're going depth first into that. So we go into the child of this node. Then we go to the second one, and it doesn't have any children right here. We go to the third one, and then we visit that one, and then that one, and then 4. And just to be absolutely sure, so do local layer 3. we can confirm that this is working because we're printing out 3 and then 3.1, 3.1.1, and then we move on to 3.2, which is at the same layer level as this one, right? So it's going depth first. Okay, I think I'll leave it there. I successfully made tree depth first search. I don't think I need this set, but we'll just save it just in case. Maybe we have a graph thing later. You know. And next time we will do, right? You know, I needed help from ChatGPT, but like, you know, such is life. Such is life. Sometimes you need a little help from someone, especially when you're new to programming like I am. I've only been doing it for about a year, so, and I just learned this depth first search algorithm stuff, again, from boot.dev. This is a great online course that I'm taking right now. You can see I've got a bunch of courses here. It's just about learning like back-end development, Python, object programming. Oh, this is new. Ooh, they inserted that earlier. I gotta check that one out. This is a new course. Yep, learn Go, SQL. Bunch of fun stuff in here, and so I've been learning stuff here that I've been able to apply in this project. So the more I learn on here, the more I can do here. So I created the depth first, or the tree data structure, and out of the tree data structure we can get a depth first search array out of that. And then tomorrow we're going to go more into how we're going to turn this tree class into something specific for layer, which will have some layer methods on it. It'll basically wrap the tree data structure in a way that will make sense for layers. You know, so it'd be like add layer, whatever, add, and then we'll have, yeah, because sometimes you want to add an object too. That'll be another thing. We're gonna have to. There's gonna be layers and objects are gonna be their own like collection of other objects. Like a meta object. I can add a meta object. A meta object would be like a drawing that has several shapes in it, and a layer could have several objects in it, and then several, you know, individual instances of a class or something. So, okay. Oh, and then if not T, then T. No, it will always. This will always return an empty. I just want to make sure it will return an empty array if there's nothing in here, and I think it will. Yeah, that's really simple and elegant, right? I mean, that's all that is. Just go here and, you know, you visit it and you go to the next one. You go to each one, it's considered it. Easier too. And you know, nil is the root node. I could make, just to overkill it, like it would be kind of fun to do, you know, a print method that would print it out this way and this way, so you could actually see the the tree going this way, which is something they did in boot.dev that helps you visualize it when you're printing stuff out. Let's do that. So like, let's add to tree out to right. Okay, so now that we have a tree, I'm actually going to add this into the code of this. We don't need this stuff. This is just to save the code along here, so the data structures. We don't need local function. We can just actually just do this, I think. Yeah. Wait, local. Do local first. Let's do that. Okay, it's still working. Okay, we'll pick this up tomorrow. That was great. All right, good stream. Thanks. Peace.